All right, welcome to lesson number 3 about different but same elements, isotopes. Okay, this is our topic number 3. So what exactly is isotopes? So we've talked about this back in lesson number 1 when we talked about John Dalton's atomic model, right? He said all the same elements are identical, but it's actually not true. It was proven to be wrong in this lesson. So right here, some atoms can have different numbers of neutrons, and those atoms are called isotopes. So iso means same, and topes is like place. So it's the same place on the periodic table. It's the same element, but they're not the same. Okay, so isotopes are basically just atoms with different numbers of neutrons. They behave pretty much the same, so they have identical chemical behavior. However, they have different masses, so that means they will have different physical properties. And also, some of them can be radioactive. So, atomic mass is the weighted average mass of all naturally occurring isotopes of an element. That does not include any man-made type of elements. That's why on the periodic table, when we look at these ones, these elements, we'll talk more about these, but they are made in labs. They're not real, well, they're not naturally occurring elements. That's why their numbers does not have decimals. It's just a whole number. However, naturally occurring elements, for example, carbon, has decimals. How come their numbers are not a whole number? Why do they have decimals? So it's because of isotopes. Okay, so the atomic mass is the total mass of all isotopes, all naturally occurring isotopes. So the idea of isotope was proposed by Frederick Soddy. He said isotopes are atoms of the same element but different masses. So again, if they are the same element, they have to have the same amount of protons. And if their masses are different, that means their neutrons must be different. Okay, so that's what essentially an isotope is. So let's look at this example. So hydrogen is a special element. Okay, so hydrogen is always a special one. Look at it on the periodic table. It's part of the green color because it is part of nonmetals, but it is isolated in a corner. So hydrogen has always been a special element. Okay, and it's the first element. So just remember, hydrogen is special. All the isotopes of hydrogen have their own names. So we got protium, deuterium, and tritium. So all the other elements, their isotope does not have a name. It's just a number. But hydrogen does have individual names for the different types of isotopes. So number 1 and number 2, these two hydrogens are naturally occurring. And number 3 in red, this one does not occur. Well, it does occur naturally, but very small amount, so negligible. Okay, we can ignore it. So yeah, I think this one, this is the radioactive hydrogen, and the other two are not. So the normal water that we drink with H2O, that's the normal protium. And then there's also some deuterium, about 1%. Okay, so actually less than 1%. So deuterium, if we have, you can actually buy this on eBay or like, I think it's eBay or Amazon or Etsy. So you can buy literally a bottle of deuterium water or heavy water. So they behave the same, taste the same, but if you drink too much of heavy water, it's not good for you. It can stop a lot of biological processes in your body. Also, deuterium if you freeze it into ice, that heavy water ice will sink in normal water because it's a lot denser and heavier. But normal ice will float on top. So that's an interesting fun fact. Here is another example of an isotope. So we got chlorine 35 and chlorine 37. Essentially same thing, 17 protons, 17 electrons, 17 protons and 17 electrons. They both have exactly the same amount of protons and electrons. The only difference is the number of neutrons. So chlorine 35 have 18 neutrons, and then chlorine 37 have 20 neutrons. That's the only difference, okay? They behave chemically the same, just one is heavier. It has a few more neutrons. That's it. So looking at isotopes, there are two different types of notations we can write them as. So this one, for example, is carbon. We can write it in the hyphen notation. So this one is basically separated by the number of protons and neutrons added. So carbon 12 is basically 6 protons and 6 neutrons. Remember, the number of protons does not change. So all of the carbon isotopes, they will have 6 protons. But neutrons will be different. This one have 6 neutrons, 7 neutrons, and then 8 neutrons. Okay, so 6 plus 6 is 12. This one is called carbon 12. 7 plus 6, that's 13, carbon 13. 8 plus 6, that's carbon 14. So carbon 14, you probably heard of it from carbon dating, right? We can literally figure out or calculate how long something has been. So remember, all living things will keep on absorbing carbon because we have to eat food. Trees are basically absorbing CO2, so that C is carbon, right? So it's constantly pulling in carbon from the air. So even humans, when we die, we will stop taking in carbon. So naturally, there are a lot of carbon 14 in the air or in the environment. And once we die, that's when we stop taking in carbon 14. And then from there are half-lives. And when the carbon starts to decay, scientists can literally measure how much carbon 14 still remains in that piece of item. For example, a mummy or a piece of art that's on paper, right? Paper was once alive, so it has carbon. So they can test the amount of carbons to find out how long ago this thing was alive. So that's carbon dating, okay? So that's an interesting fact with isotopes. So very useful stuff. And then we have the nuclear symbol notation, okay? This one, we have the atomic mass number on the top. So unlike periodic tables where you have the atomic numbers on the top, this time they're flipped. So it's kind of confusing. I don't understand why. They could have just left it the same way as the periodic table. But here we go. Atomic number now is on the bottom, and the mass number now is on the top. That's basically it. That's the nuclear symbol notation. Super simple. Let's look at an example. Before we look at an example, let's look at this periodic table. So right here, there are a bunch of naturally occurring isotopes, and this periodic table pretty much gives you a summary of these isotopes and kind of explains why the atomic mass on the periodic table always have decimals. So right here we have different isotopes of iron. We have iron 54, iron 56, iron 57, iron 58. The numbers in red, those are naturally occurring radioactive isotopes. So we got cadmium 113, platinum 190. So there you go. So here is a simplified version of how we find the atomic mass. Okay, so naturally I'm going to round it, so it's a number we can easily understand. So let's say we have 99% of hydrogen in nature is just normal, H1, okay? And then there are 1%, it's less than 1%, but round it. It's about 1% H2, deuterium, okay? So what we do is we just add it up. So the sum, this is the summation sign in for math. It's called, what is it called? It's not epsilon, it's sigma, okay? Sigma, this is the sigma sign. So the sum of every isotope. So for example, 99%, you can't put 99%, you gotta put 0.99 times 1 AMU. And another one is 1%, which is 0.01 times 2 AMU. And then if you plug this into your calculator, you get 1.01 AMU. Okay, that's why on the periodic table, let's look at the periodic table. Here we go. We have 1.008. Okay, so it's about 1.01. So that's how we find those atomic mass on the periodic table. Okay, but this is the actual numbers. So the hydrogen of protium naturally occurring is about 99.98%, and then hydrogen 2 deuterium is about 0.015%. So if you plug in the AMU mass in here, this is how we get the 1.008. Okay, this example is just simplified, so you understand. But we're never going to calculate this. I'm never going to ask you to calculate the average mass of any element. I'm just showing you how we get these decimal numbers. Okay, let's do some practice right here. So write the isotope notation as well. Oh, this is already there. So we'll have chlorine 37. So the number of protons for this one would be 17. Remember, the number of protons is the atomic mass. And for the nuclear notation or the isotope notation format, the atomic number is on the bottom. So we have 17 protons and 17 electrons. They always balance each other out. And then the neutrons is basically the mass number, 37, subtract the number of protons. So 37 minus 17 equals 20. So this one have 20 neutrons, okay? So it's a little bit different than the numbers on the periodic table. Same thing for this one, we got Mg12. So 12 is our number of protons, and then 12 is also the number of electrons, and then the number of neutrons would be 28 minus 12. So 28 minus 12 equals 16. Okay, so we have 16 neutrons for this one, Mg28. The isotope notation with the hyphen, this one would be called chlorine 37 or chlorine 37, and this one would be magnesium 28, Mg28. Okay, let's do another practice. So fill in the following table. So right here we have oxygen, and we need to find the number of protons, electrons, and the mass number. So they're all in the hyphen format. So let's do this. Oxygen, how many protons does it have? Let's check on the periodic table. So oxygen has 8 protons. This number does not change, okay? So we will fill in 8 protons for oxygen. Why is it not working? Okay. And then 8 electrons. The mass number, again, is the number of protons plus neutrons. Electrons are 0. We can ignore the electrons. So this one would be 18 AMU. So the hyphen format would be oxygen 18. Or you can write it as O18 with an 8 atomic number on the bottom. Okay. This one, it tells us the number of protons, then the electrons will have to be the same, 33. And the mass number would be 33 plus 42, 75. Okay. Question is, which element is this? So let's check on the periodic table. So let's look at atomic number 33. That would be this one, As, arsenic. Okay. So arsenic, A-R-S-E-N-I-C, arsenic 75. And the other format would be As 75 with 33 on the bottom. Okay. And then the last one, we have 31. This is the mass number. Okay. So the hyphen format, this one's the mass number. So mass is 31, proton is 15. So the number of neutrons has to be 31 minus 15. That's 16. Okay. And then the electrons will be the same as protons, 15. And which element is this? Let's check on the periodic table. Element number 15 is phosphorus. Okay, P. Oops. Why is it not writing? Phosphorus 31. And then it's going to be P31 with 15 on the bottom. This is how we do these type of questions. Okay, so I might give you practice problems like this, and this is how you fill in the table. Lastly, besides neutrons changing, just remember that protons will never change. They don't change. If it changes, that's nuclear chemistry. We're not there yet. They don't change for now. Just remember that. Neutrons can change. When neutrons are different, we call them isotopes. Okay, we just learned about this. And then electrons can also change. We're going to learn about ions next unit. So this is our lesson number 3.